All right, take a look at our first section for this week, which is 6.3. So we're pretty much just going to do 2 sections this week. 6.3, we'll split it into a few days. And then 6.4 will be a little bit more on graphing, but it'll be functions that aren't sine and cosine. So the 2 we're going to start out looking at, sine x and cosine x, fall under a special category of functions, and they're called periodic functions. Nothing we've studied up to this point has been a periodic function. We've studied radicals, we've studied logs, exponentials, quadratics, linear equations, rational. None of those are periodic. Periodic has to do with when you graph it, you see a pattern repeating over and over. So let me just show you first. So let's put a picture up of what sine would look like. Okay, and there's a picture of a sine wave. We look at sine and cosine in the same lesson because they pretty much look the same. All right? All the other trig functions look completely different. They don't look anything like a wave at all. All right, let's take a look at that. So if we go back, the next thing I'm going to say is that the y values repeat. Okay, the y values are going to repeat themselves over and over for a certain set of x values. All right, so basically, once you move a certain amount on the x-axis, you're going to see a set of y values you've already seen before. Okay? And that's what I'm going to show you on the next page with that graph. Okay, so all the y values, they just keep repeating in the same order over a certain set of x values. All right, so first of all, when you're looking at a graph like that, the x-axis, that's your angle. That's how you would label it. Usually we use theta. The y-axis, in this case, I think I did, let's see, I did sine. So your y-axis represents the sine of theta. So the x-axis is what's theta, like 90 degrees. And then the y-axis is, okay, well, what do you get when you plug that into sine? What's the sine of 90 degrees? So if I trace this section right here, that one section that I just traced, that describes the entire graph. Because all you would have to do is take that. You could copy it. Let's go like that. Put another copy next to it, and you get the next section of the graph, okay, which there's a better name than section, but that's just what I'm calling it right now. So go back for a sec. So the y values repeat over a given set of x values from, let's do this in blue, from here to here, where I just put those 2 marks. That's the given set of x values. That's kind of how far you got to go on the x-axis before you start seeing the graph repeat. And you could adjust that. You could kind of slide those 2 markers left and right, as long as you keep them, in this case, 4 units apart. Okay, and what we're looking at here, this graph is in radians, right? So that would represent 0 radians. And that would be the end of our first, it's called a cycle. Okay, that's the end of the first cycle. Does anyone remember, like in a circle, how many radians to go all the way around the circle, and then you get back to exactly where you started? Katie?
Is it 2?
Close. Yep. 2 pi. So that's kind of what's happening here. You're starting here. You're going along that wave, and now you're back exactly where you started. Well, if that's 0, this would be 2 pi. So that's how, I'm gonna write that kind of nice in a sentence in a second, but you have to go 2 pi units before your graph will repeat itself. In other words, you got to go from 0 to 360. Now, you can change that. If you had a graph that looked like this, well, that's different. Now you've compressed it. So the graph is going to repeat faster. Same thing if you did this. That's a graph that's been stretched out. So you might have to go further than 2 pi before you see it repeat. And we're going to have to figure that out. Like, if you stretch it, how far do you have to go before you get to the end of the cycle? Do you got to go to 4 pi now, or 6 pi, or 8 pi? Like, how much bigger did you make it? And we'll figure that out. Okay, so the length of that interval that you got to go before your graph repeats, there's actually 2 names for it. I think I mentioned both. I said it was called a cycle. It's also called a period, 1 period of the graph. Just to make it clear, what's in red right there, that's exactly 1 period of the graph. And usually when we sketch a graph, all I'm going to ask for is 1 full period. Because if you can sketch 1 cycle, then all you got to do is copy and paste it over and over, and you can make your graph as big as you want. But for sine and cosine, one period is usually good enough. And the basic period, if you don't mess with it, you don't stretch it, compress it, you just graph it, just like I did, just basic function. The basic period is always 2 pi radians, or 360 degrees. That's how much your angle has to go through before your graph starts repeating itself. Okay. And the other name, I already mentioned this, but a period is also called a cycle. We usually call it a period, but cycle is used. Other areas use that. Is anybody in electrical? You're in electrical? So when you measure, not the voltage of an outlet, but like something else you can measure about the outlet, and this has to be correct, otherwise when you plug things in, it won't work right. Do you know what the other thing is you measure?
The current.
So there's the amount of electricity there, the current, and the current has to have a certain, it has to do this at a certain rate. And if it doesn't, things are going to not go well for us. At least for alternating current, because that's alternating, it's up, down. But it has to go kind of up and down at a certain rate. And different countries do it different than the US. Yeah? So amperage measures the amount of current. Yeah?
Hertz.
Exactly, hertz. So when you have an outlet like in your house, or like the ones in this room that computers are plugged into, they operate on 60 hertz. And hertz means cycles per second. It's how many times the electricity is oscillating up and down per second. So most outlets in the US operate on 60 cycles per second. And if you had a maybe like a multimeter or some kind of device like that, you could actually plug it into the outlet and you could see a picture, something like that. It would show you a picture of the electricity. Okay, and ideally, that's what electricity should look like. Perfectly like clean, good electricity should be a nice sine wave. If you've ever run something on like a generator, you might notice sometimes they warn you about like computers or TVs, especially if it's like a cheaper generator, not to plug it in because it could damage it. And that's because if you looked at the electricity that comes off a generator, it's almost a little bit more square, the way the wave looks. So instead of a nice smooth wave like that, you might get something a little more kind of like that. So what that's called is it's a modified sine wave. It's kind of close. It's actually easier with electrical components and cheaper to make an electrical wave like that, but some things don't like that. something like a light bulb, it'd probably be fine. But especially like motors, like I can tell like my boiler, furnace in the basement, has a motor on it, and I can tell when the motor's on. When it runs on the generator, it just sounds a little different to me. I guess I'm just used to what it normally sounds like, and then I hear it, and it just sounds a little off. That's because my generator doesn't, it's not exactly 60 hertz. I think it's like 58 or 62. It's close, but it's a little off. So that's one area that you see cycles per second when they talk about electricity. But we'll pretty much stick with a period. Okay, so any questions on that so far? All right. So let's take a look at the graph of sine negative x and then negative sine x. See what the difference is. Now, from a transformation perspective, what happens when you put a negative either in front of the x or out in front of the function? Negatives cause a graph to do what? Yeah. Flip or reflect. When you have it inside, that's all your horizontal stuff. That's a horizontal reflection. When you put it outside, that's a vertical reflection. So let's take a look at the difference between y1, which is flipping it inside, so that's a horizontal, or y2, which is flipping it vertically. Okay, so let's graph it. Let's see what it looks like. That is a little different than the wave I just had on the screen before. If you look closely, you can see that. But what I want you to watch is what's happening right now. What's the difference between when I put the negative on the inside or when I put it out in front? Okay. Nothing. They're the same thing. So what that means is this graph is symmetric about the origin. So there's a symmetry to that graph, and it's all centered around the origin. Another way to kind of think about that is if you it's a little hard to explain, but if you took this piece right here and you broke it off and you rotated that piece that's circled 180 degrees, it would land exactly on top of the left-hand piece. Okay, so if you can do like a 180-degree rotation with half of it, that means it's symmetric about the origin. This would land right here, this would land up here, that would land right there, and so on. Okay, let's do the same thing with, or a similar idea with cosine. Let's graph cosine negative x and cosine positive x. So cosine negative x, cosine positive x. So this is the first time we've seen the cosine, but it looks kind of the same. It's a wave. So there's cosine negative x, there's cosine positive x. Ashley, what's the difference there?
They look the same.
They look the same, but notice it's not quite the same idea. The one above had a negative inside and a negative in front, and they were the same. This has a negative inside and then nothing, and they're the same. So what that means is this graph is symmetric over the y-axis. Most people can visualize that a little easier than symmetric about the origin. If you took this, if it was a piece of paper, and you folded it right there, the left-hand side of the piece of paper would land exactly on top of the right. So that's symmetric over the y-axis. And both of these come in handy, especially the second one. We're going to use that later on, because if I ever asked you to find the cosine and it happens to be negative, so that's the cosine of negative 25 radians. Well, it's exactly the same as the cosine of positive 25 radians. The negative doesn't make a difference with cosine. You can just get rid of it. Right? So we're going to, when we get into more like numerical calculations, that's going to kind of help us. The top one, this is showing you can't get rid of a negative when it's inside sine, but what you can do is put it in front. Because what we don't like is this. We don't like to ever have negatives inside the argument. Okay? We can put a negative in front, that's better. But we usually don't like the inside number to be created. So there's a couple ways we can solve that problem, at least with sine and cosine. Yeah, let's just take a quick look at tangent. Does anyone remember what tangent equaled? Like it was something over something when we did the identities last week? Yeah?
Or wait, no, that's
that's right triangle trig. So I'm thinking in terms of trig functions. It's this over this, yeah?
sine over cosine.
It's sine over cosine. Now look at cosine. It's right here. Cosine hits that number. Well, it hits it an infinite amount of times. But what is that number that I just put all those dots on? The y coordinate of all those points. Yeah? 0. Now we just said tangent is sine divided by cosine. What number are you never allowed to divide by?
0.
You're never allowed to divide by 0. But the cosine function is 0 at some points. Right? It's 0 at infinitely many points at regular intervals. So that's going to lead to this graph looking a little funny. Right? What do you think is going to happen in the graph of tangent? Like if you go to draw it, we've talked about trying to draw these kinds of things before. Like if you use your pencil and you're drawing it. This one has a special property that no other trig functions do. Just sine and cosine have this. Yep.
Is that like a hole that's
A hole, or there's some kind of discontinuity. So these graphs, you can't draw them unless you pick up your pencil. All right. So let's just take a look at what tangent would look like. And what's the other option? Besides a hole, you could also get a what at the when something is 0. You divide by 0. We studied these a lot with rational functions. And we used the calculator to check what was happening on each side of them. Oh, Joe, you remember? When we used the calculator, we checked the value very close to it. We might check 2.001 and 1.99. That happened not on Monday. Anyone remember it? Tori? Asymptotes. So the other thing that can happen is when you divide by 0, maybe it's a hole, but it could be an asymptote. This ends up being an asymptote because there's no common factors in the numerator or denominator. So that's what tangent looks like. So it's definitely a pattern, but it's a discontinuous function. Same with secant and cosecant. I think the last problem on the test, we learned that cosecant was 1 over cosine. Secant was 1 over, wait a minute. Secant was 1 over cosine. Cosecant is 1 over sine. Well, if you put sine or cosine at the bottom of a fraction, you're going to have some problems when you graph. So just to show you what secant would look like, you get asymptotes again. You get these kind of U shapes and N shapes that just keep repeating. If you look at the range of that, it's pretty much everything that cosine isn't. Cosine is trapped between -1 and 1. This one is everything outside of -1 and 1. All right? So there's some kind of connections between the ranges. But we'll talk more about these other functions on Thursday. All right, so whenever you want to make a graph of sine and cosine, we're going to do that a little different than we would do tangent, cotangent, secant, and cosecant. Okay, when we start getting into those other ones, we have asymptotes. So we're going to have to sketch the asymptote, check the behavior on each side, kind of like we did before. But sine and cosine are continuous. So we don't have to worry about asymptotes. But what we need is about 5 points. Generally, we like to figure out where it starts, where it stops, and then the halfway point. And now you've got all 3 points in one cycle for where it crosses the x-axis. You've got all the x-intercepts. So we want to get all those. And then we want to get the high point and the low point in that cycle. That's pretty much what we do every time. Get the intercepts, get the high point, get the low point, and that's enough information. Just remember, when you sketch it, it should look curved. Nothing about these graphs is straight or a sharp turn. Now, if you do it exactly like I said it, you're going to end up with 5 points that are all pi over 2 radians apart, or 90 degrees. So you've got 0, 90, 180, 270, and then 360, you're back at the beginning. So you could look at 360 as the end of this cycle or the start of the next one. It's both. Okay, but notice how I labeled my axes here. We're usually not going to label the axes like 1, 2, 3, 4, because the numbers that we work with in radians are pretty messy. Like that's 1.57, 3.14, 4.71, 6.28. So what we're going to do is we can label the x-axis any way we want as long as we're consistent. Like 2, 4, 6, 8, that's fine. Or this is even better. We're going by pi over 2 each time. So 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. That's the pattern. Any questions on that idea, finding those 5 points? We'll explain more how to do it, but just kind of any question on the goal? All right. So anytime that we graph sine or cosine, the way we're going to do it is we're going to start with this original table. So these tables are going to be our starting point. Once we know where a graph is going to start, we can figure out where it's going to move to. But we got to know where it starts first. So this is your starting table for sine, and it's exactly the picture I have right here. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 2 pi, you're back at 0. Okay, and I don't have a picture of cosine up there, but let me just do it on the calculator again. We're going to focus just on the first cycle. Okay, so looking at the first cycle of cosine, what's y? When my x value is 0, what's the y value for cosine? Robin?
0. Wait, no.
So this one
1.
doesn't go through the origin. Yeah, this one is 0, 1. So when you're at 0, for an x value, the cosine of 0 is 1. Chris, how about when I'm at 1? Or I'm sorry, when I'm at pi over 2, which is my first tick mark. That'd be what?
1.
So you're saying we're up here? We're at 1, 1? Or pi over 2, 1?
Yeah, no.
Not for cosine. For sine we are.
Probably 2.
So 2 would be up up about here. Yep.
-1.
So when we were at 0, we're at 1. That was the first one. So the next one is when we're at the first tick mark, which is pi over 2. 0, yeah. So pi over 2, 0. And then pi is the third one. What are we at when we're at pi? -1, there we go. All right, so let's just write those down. So pi over 2, we're at 0. Pi, we're at -1. 3 pi over 2, that's my 3/4 mark. 3/4 of the way through the cycle. I'm back at 0. And then 2 pi, I'm at the end of the cycle, and I'm back where I started. Now, if you were sketching that, try not to make it look like a V. Right? Those dots, they kind of look like they would make a V, but remember, it's part of a cycle of a wave. So just try to give a little curve to it. So that it shouldn't look like an absolute value. So those are always your starting tables for sine and cosine. We're going to start off with some pretty basic ones today and tomorrow. We're just going to do one transformation per problem. Meaning maybe we'll just shift up and that's it. We're not going to put like a shift up and a shift left in the same problem till we get to Wednesday. So what that means is if we're only going to do one transformation per problem, when you're doing your new graph, figuring out where your graph moved to, one of these columns always stays the same. Because we're either going to do something to the x's or something to the y's. Not both. Not until Wednesday. That's what I just said. Okay, as long as your problem only has one transformation in it, you're only going to affect the x's or the y's, not both. All right, so everything I just explained to you was pretty much kind of like background information about sine and cosine. Now I'm going to focus specifically on two transformations. The first one is a phase shift. Sine and cosine waves have lots of applications to things in real life, like electricity. That's a little complicated to demonstrate in here. But another thing they have a connection to is sound. And sound is something that I can demonstrate. So for the transformations that you can hear, I'll play them so you can hear what it would sound like. 3 out of the 4 that we do, you can hear them. The fourth one, I don't know of any connection with that with sound. But the other 3 I do. So and this is one that you can hear. So phase shift, it's just when your graph is translated left or right. That's all it is. It's a horizontal shift. So we've seen that before in something like this. That's a horizontal shift of a square root function. There's a horizontal shift of a log function. There's a horizontal shift of a sine function. So anytime you add or subtract inside the parentheses, that's when you have a phase shift. Now, what would this +2 do to all of them? It would shift it 2 units which way? Left. Remember, it's always the opposite. Okay, and I think I write that down in a second. Okay, so phase shift could be plus or minus. Plus or minus just controls which way it's going to move. If it's x minus a number, you've got to remember minus shifts everything to the right. If it's x plus a number, like the example I have up there, that's when everything shifts left. And that's exactly the same as everything we've studied all year. So remember in this case though, A, right? You're shifting left and right. What's the name of the axis that goes left and right? I mean, I know it's the x-axis, but what does it represent in a trig function? Yep.
The angle.
It's the angle. So A is a shift of a certain number of degrees or radians. So when you shift left and right, you're shifting by an angle. And usually we don't shift, I mean, technically you can shift by whatever you want, but the common shifts that we do are a 45-degree shift, a 90-degree shift, and a 180-degree shift. Those are just the ones that come up a lot. Okay, any question on that? So let me just show you visually what that kind of looks like, and then we'll play something and see if you can hear what a phase shift sounds like. Not that. All right, so let's take a look at this. So what this program allows me to do is just generate different types of sounds, including doing a phase shift. So what it looks like is like that. So the red wave is sliding left and right, and the blue wave is staying right where it is. Notice that if you shift it 360 degrees out of phase, it's pretty much like you didn't shift it at all. The wave lines back up with the next wavelength, and it's back in phase. So anyone have a guess what's going to happen when I play it? Because I'm going to play it as I play it. I'm going to keep it on the whole time and slide it. Have a guess what you might hear? Oh, Justin?
No, I don't know.
Any thought at all?
Not sure.
Not sure, Robin?
A high-pitched noise.
Okay, so like you might hear a high-pitched noise. All right. Any other thought what might happen? So you're thinking the pitch is going to change? Like it might go low to high?
I think high to low.
Or high to low, so it's going to start out like high and then get low. All right. Any other thought? Well, what else can change besides like the pitch of a sound? You could also hear a difference in the
Speed of it, or like how fast is it going to be like a steady?
It's going to be on steady the whole time, yeah. And as far as the speed of the sound, the speed is pretty much a function of the air temperature in this room. So air temperature in part and what the sound is traveling through controls how fast it is. So like for example, if you have a really long piece of metal, say you had a piece of metal 2 miles long, if you had a hammer and you hit that piece of metal and somebody had their ear on the other end 2 miles away, they would hear it through the piece of metal first, like having your ear right on it, and then if they pick their head up quick, they would hear it again through the air, because sound travels faster through solid objects than it does through air. Same thing underwater. Sound travels faster underwater than it does in the air. But again, it depends on air temperature a little. So, what else can you hear a difference in the sound besides the pitch of a sound? What else can you change about a sound? Yeah?
The volume.
Yeah, you can change the volume, like how loud it appears, or how loud we hear it. So let's play it and see what happens. So what I'm going to do is I'm going to play this sound. Just give it a second. And I'll turn it up just a little bit. So it's not a horribly high-pitched sound in terms of what humans can really hear. There's the sound. And now what I'm going to do is I'm going to change the phase of it as I play it, and I'll let you maybe try to describe what's happening. All right. So as it played, what did you hear? Yeah.
It went like quiet to loud to like quiet again.
So it was like quiet, it got louder, and then quiet. Yeah.
And it like when it got louder, it was I don't know how to like just like, I think my hand is the thing I'm using to describe it. Like, kind of like, yeah.
So why don't, if I drag it, can you tell me when you think it's at the loudest? And just tell me to stop.
Okay.
All right, so I'll turn it on again, and you just tell me.
Like right there.
So it's loud right around 228, okay.
And then it goes back down.
So like,
And then it goes back up.
it goes back up. All right. Now, was it quiet or was it the quietest around 228 for anybody?
That was the quietest.
That was the quietest to you. What? Yeah?
Does it depend where you are in the room?
Yeah, depends where you're sitting. So phase is a little bit complicated to explain, but basically the idea is, for me, I didn't hear anything, okay? Because I was standing almost right in the middle of the speaker, directly under it. I didn't hear any difference the whole time, standing in this spot. But again, that has to do with the acoustics of the room. So when you've got a wave like that, compared to, let's draw this one. Let's try a different color. Depending on where you're sitting, all of a sudden what happens at some points is the wave is like that. And when the wave is like that, again, it might be a different amount of phase shift for different people, depending on where you're sitting. But what's happening here is the green wave is at the height, the black wave is at its lowest value, and they're fighting each other. So if you were to basically find that y value, and add them together, it's kind of like they cancel out at that point. So that's why it sounds quieter. Now, it won't sound completely quiet because it can echo. And that's also what you're hearing. So you're not only hearing the sound, you're also hearing probably 7 or 8 echoes of that sound at the same time, which you can't really distinguish between because this room is so small that the delay in the echo, it's almost instant. But you're hearing an echo, even though it's not like you yell like a mile away and then you hear it come back. It's a little different. But if you could do this same thing without any walls, like if you could do it outside, there would be a point where the sound would almost disappear, if not completely disappear, if you stood in just the right spot outside with no echoing at all. It's like a big field, 2 speakers, and you could kind of do the same thing walking back and forth between the speakers. You might walk and all of a sudden you find, oh, that's a really loud spot, and then you keep walking and then like, oh wait, now that got softer. So those soft spots where you couldn't hear it as well, those are the kinds of things that, like when they design a music hall, they want to avoid that. So if there's a spot where Robin was sitting and it was very quiet, that means that if the sound was coming from here, the people in that area wouldn't hear things as well. Although other people in a different area might hear it just fine. So they try to make it so the echoes and different things are kind of reduced, in the dead spots. They also have a switch on the speaker hanging up. That's the subwoofer speaker. There's a switch on there that says phase. So what you can do is, if you put that speaker in a certain spot in your house, and it doesn't sound good where you're sitting, because usually you sit in probably one of, same spot when you listen to music most of the time, you can flick a switch on there so that it'll sound better where you're sitting. Maybe it won't sound good somewhere else. So it'll move the bad spot somewhere else in the room, but it'll sound good kind of in the area where you like to sit. And I forget the name of it, but I think it's just called phase. Phase A, phase B. And you can just try both and see which one sounds better. So yeah, phase, kind of an interesting idea. We hear it as like a volume change, but I didn't change volume at all. Even though it sounded like it got quieter and softer, it was like waves kind of interfering with each other. All right, so when we do a phase shift, we want to figure out, all right, we knew where the graph was, where is it moving to? So phase shift is, which direction was it? Horizontal or vertical?
Horizontal.
It was horizontal. So that means the y values are not changing. So to figure out your new y values, all you have to do is go back to one of the original tables and copy the original y values down. Now, which table do you use? Depends on if you're doing a sine or a cosine problem. So if the y's are going to stay the same, then your x's are all going to change. So what I want to do is let me put up the first example we're going to do, and I can just kind of reference it when I explain step 2, and it'll make more sense. All right, so to find your new x values, first thing you have to do is look at what has been added, or in this case, subtracted. Okay, so my argument there is x. I've subtracted pi over 2 from it. So that's what I've done in this problem. So I think back to what we just wrote in the notes. Okay, I'm just going to go back to it for 1 second. Yeah, I can keep that up at the same time. When you subtract something from the argument, the graph shifts to the right. So I think, okay, how can I make x values all go to the right? I have to make them bigger. Right? If you make an x value bigger, it's going to go to the right. So when we see a minus pi over 2, we're going to do the opposite of that. We're going to add pi over 2 to all my x's. And that's going to shift everything to the right. So you look at what you've added or subtracted, and you do the opposite of that. Now you've got to be careful because this is 4 transformations. 2 transformations, you do the opposite. 2 transformations, you don't. Phase shift is one of the transformations, you do the opposite. So you just have to remember that. Where you start running into trouble is when you do the opposite when you shouldn't be. Okay? But this is one that you should. Okay, so let's see if we can figure out the 5 points we're going to need to sketch this graph. So Kathleen, what values could we fill in right away? Because they're not changing at all.
The y values.
The y values. So I'm going to go to my table for sine, look up the y values, and write them all down right now. Can someone remind me what my y values are for sine?
0, 1, 0, negative 1, 0.
Yep. Usually the way I grade something like that is I give you like a point for each x and y value you got right. So there'd be 5 points right there. Got all the y values right. Now we're going to get all our x values. So I'm going to start with the originals, and then I'm going to do something to them. So my first x value is 0. What's my next x value for the originals? Pi over 2. Yep, third one.
3 pi over 2.
That's the fourth one. So pi. And the last one. 2 pi. So I wrote those off to the side a little bit because now I left a little room to do a calculation. What am I going to do to all 5 of those x values? Yep.
Subtract pi over 2. Or add pi over 2.
Add pi over 2. All right, so let's do that. So add pi over 2, pi over 2. And what this is doing is you're making all the x values bigger, so you're shifting them all to the right, which is exactly what should happen when you subtract. All right, plus pi over 2, plus pi over 2. Now, where I'm putting a box around right now, that's where all my final answers are going to be. Okay, so let's go through them. Nate, what's 0 plus pi over 2?
I'm just going to assume pi over 2.
Pi over 2, you sure?
Yeah.
Yeah. So no common denominator there. You don't need anything fancy. It's just pi over 2. Next one already has a common denominator. Pi over 2 plus another pi over 2 is how much? Yep.
1.
Not quite. If you had like 1/2 plus 1/2, that would be 1. But this is still going to have pi in it. Still going to have pi. Emma?
Would it just be pi?
Yeah, it would just be pi. Now, if you say, well, wait, shouldn't it be something over 2? Yeah, it's 1 pi over 2 plus 1 pi over 2. That's 2 pi over 2. But 2 pi over 2 is just pi. Chris, what would be my common denominator on the third one?
2, right?
2.
Multiply first one by 2.
Yep, multiply the top by 2 and the bottom by 2. Now we've got 2 pi over 2 plus 1 pi over 2. That's 3 pi over 2. Fourth one already has a common denominator. Gabe, what's 3 pi over 2 plus 1 pi over 2?
Just 2 pi.
Yeah, it's just 2 pi. And again, if you're like, well, wait, where's the denominator go? 3 pi over 2 plus 1 pi over 2, that's 4 pi over 2. But we should reduce it to 2 pi. And the last one, it's going to have the same common denominator as the third one. Everything here is a common denominator of 2. So if you double the top, you get 4. Double the bottom, you get 2. Right, so Ashley, what would my last value be?
2 pi?
So the fourth one was 2 pi. But this one, what's 4 pi over 2 plus 1 pi over 2? Quite. What if you just take the pi out of it? What's 4 over 2 plus 1 over 2? Exactly. So 5 over 2. But this one has what in the numerator with it? Pi. So it's going to be 5 pi over 2. Now, another way is you'll start to see a pattern. If you had written all these with a denominator of 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. The next one would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2, if you were going to draw the next cycle. And the y values, to go with the ones I just said, would just keep repeating 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0. Those would just keep repeating over and over in the y column. Okay, so that's the hard part. So what I usually do is give you 1 point for each of those, so that would be 10 points for that problem. And now the last thing is just to make a sketch. So on the y's, I don't need to go any higher than 1. I don't have to go any lower than negative 1. So we'll start with that. And I'm going to label my x's using these values right here. The only condition on labeling your axis is that you're consistent. Make sure you don't basically do something like this. 1, 2, 4, 5, 6. You can't all of a sudden skip a couple numbers and then go back to going by ones. Right. It's the same idea. These are all 90 apart if you did them in degrees. 90, 180, 270, 360, 450. It's just not as obvious because most people aren't used to seeing them in radians. But they're all nicely spaced. So pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. And it's probably a good idea to move them a little lower. If you didn't, it's fine. You're just going to end up drawing through your labels when you make your graph. Okay. So now we graph it. Pi over 2, 0, and then 1, 0, negative 1, 0. 1, 0, negative 1. It's easier on the test and on the worksheet. It's actually set up with a grid or there's dots so you can kind of see what you're doing. And there's your sketch. Okay. If they wanted to know, well, what would the original graph look like? The original graph is the same every time. that would be your original. I'll just do it in a different color. There you go. So I did the original in red, and I did the new one in black. So it shifted it right 90 degrees. So that's a 90-degree phase shift, or pi over 2. Okay. Any questions on that? All right, so the only thing that's kind of a pain about that is you got to deal with the fractions with pi. Let's do a cosine. Okay, first of all, if this was a test problem, I'd have to figure out what kind of transformation it is. It's adding, it's inside, so I know it's a phase shift. Phase shift, I know is going to change the x values. So the y's can all stay the same. What are my y values for cosine? The originals, yeah?
1, 0, -1, 0, 0, 1.
That's half your table. That's the easy half. So we got those done. What are my original x's? And in this case, it doesn't really matter if you use sine or cosine. They're the same. Oh, what?
Would be pi over 2. Okay. So pi over 2,
Mhm.
2 pi. Can't remember.
Can't remember. That's okay. Yep. Kaya.
0,
Yep.
and then 3 pi over 2 and pi.
So yep. 0 pi over 2 pi. 3 pi over 2 2 pi. And now I'm going to do something to all of them. What am I going to do to all those values, Chris?
Subtract pi.
There you go. Subtract pi. Now, 3 of those are pretty quick. 0 minus pi is negative pi. What's pi minus pi?
0.
0. 2 pi minus 1 pi?
Pi.
Just pi. So there's those 3. And now the other 2, well, there's a couple ways to do it. You either just find common denominators, or every point, if you average 2 points, the third one is going to be the one that's right in the middle of it. Because all of these points are equally spaced. So technically, you could just take 0 and pi, average them, and that's the one that's in the middle. Or if the average thing seems confusing, just find the common denominator. So I'll do it both ways. For the first one, I'll find a common denominator. Common denominator is 2. Multiply by 2. Multiply by 2. Madison, what's pi over 2 minus 2 pi over 2? Negative. Anything else?
Over 2.
Negative pi over 2. Yep. And now this one, I'm just going to average the one above and below it to get the one in the middle. What's the average of 0 and pi? Yep.
1/2 pi.
1/2 pi, which is the same as saying take pi and divide it by 2. That's half of pi. Third way is you could look at a pattern. That's negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2. The next one would be 3 pi over 2, 4 pi over 2, 5 pi over 2. Just keeps going like that. Okay, that's it. That's my table. Now let's make our sketch. All right. So this time I'm going to put negative pi right there. That's like negative 180. And I should move those labels down, which I will after. That's negative 90. 0 I don't need to label. That's the axis. Pi over 2 is 90. And then pi is 180. Good enough. Okay, highest and lowest, it's always 1 and negative 1. If you don't shift or stretch the y-axis out, it's always 1 and negative 1. And now we're just going to go 1, 0, -1, 0, 1. So 1, 0, -1, 0, and at pi we should be back at 1. Now remember, that's part of a wave. So try not to make it like a V shape. Try to make it, and it would keep going like that. You don't have to draw the dotted part, just the solid part. That's kind of what it would look like. Any questions on? All right. All right, so the last one, and then we'll do the vertical shift, which the nice thing about the vertical shift is there's the arithmetic is super easy. This is the hard one today. Vertical shift, there's no no fractions at all usually. All right, so I'm going to make the table because I just want to get into the graph. Okay? So you've got 0, 1, 0, -1, 0. You're going to subtract pi over 4 from all your x's. So you would have negative pi over 4, pi over 4, 3 pi, 5 pi, 7 pi, all over 4. Okay, so if you go ahead and subtract pi over 4, find your common denominators, that's what you'll get. Okay, let's do our graph. Let me move this up. Now, if you think of these numbers in degrees, I'm just going to write them off to the side. I'm not going to use them, but I think it's going to help you to see something. That's negative 45. That's 45. 135, 225, 315. They're all 90 apart, just like they always have been. But let's say we put negative pi over 4 right there. What's the axis? What do we always label that as? Like what number would it be? Well, like if you had a coordinate right on an axis, it would have a what value in the coordinate? It would have a 0. So that's 0. All right. So let's put pi over 4. Now, where would 3 pi over 4 go? Yeah? So from pi over 4, where would you put it? Over 3? Like skip, we don't have to skip that many. Let's figure out, we do have to skip though, because in degrees, how much is that section worth that I just underlined? It's worth 45. So what we've done is we've made each section worth 45 degrees. So that's 45, that's 45, that's 45. They're all 45 apart. Now, 45 and 135 are how far apart? 90. So how many sections is that? 2. So we have to have 2 sections between them. So here's pi over 4. 1, 2. That's 3 pi over 4. The next one is another 90. 1, 2, 5 pi over 4, and I think I'm 1 tick mark short. 1, 2, 7 pi over 4. So you just have to be careful when you're numbering how you set up your numbers. Okay? You skipped one between negative pi over 4 and pi over 4. Right? You skipped the axis and went to the next tick mark over, so you pretty much have to skip one every time. Okay? That usually happens when 0 is not in the x column. Notice 0 was in the x column here, so we didn't skip it. 0 was in the x column, well, I counted that as 0. So 0 would have been the label before this one, even though we didn't write it. Right? So you got to be careful. Once you set that up, the graph is easy. Okay. But I just wanted to set up the axis. Any questions on how I numbered that? You'll know if you number it wrong because it's going to look like this. Part of your graph is going to look kind of squished, and then the next part is going to look stretched when it should look like that. Okay. So if you're using graph paper, it's pretty clear when you make a mistake. All right, so last transformation we'll do, and this one's a lot easier, is the vertical shift. So one nice thing about this is that what you see is pretty much what you do. You don't do the opposite. So if you're thinking, you're like, wait, we just did adding and subtracting. How is this still adding and subtracting? Well, the difference is now we're adding or subtracting outside parentheses. Okay. A phase shift, you've got to put parentheses around the letter and what you're adding or subtracting. This will not have parentheses around the letter and what I'm adding or subtracting. It will not. And it could be plus or minus on either sine or cosine. And don't do the opposite. Add moves it up, minus moves it down. Okay. Don't do the opposite. I think for some reason people get phase shifts stuck in their head and you've got to do the opposite all the time, and people just do the opposite on everything. No. Don't do the opposite here. Okay, so when we do a vertical shift, what values are not affected at all when you shift vertically? Chris? The x values are not going to be affected at all, and that's great because the x's are all the ones we don't like to deal with. We don't have to deal with them. You don't mess with the 0, the pi over 2, the pi, the 3 pi over 2, or the 2 pi. You keep them all exactly the same. What we do have to change is the y values. But all we have to do is add or subtract whatever number you see. Don't do the opposite. To all the original y values. So this usually means we're just adding integers. Like a +2 to everything, or a -3 to everything. It's very, very simple math. Okay. So we'll try 1 or 2 of the vertical shifts, and then that'll be it. So before I even graph example 4, can someone just tell me what is the +2 going to do? Add 2 to the what?
Y.
To the y's. And visually, what is that going to look like? It's going to shift up 2. That's all that's going to happen. So it's exactly what we just said. Add 2 to all the y's. Don't change the x's. 0, pi over 2, pi, 3 pi over 2, 2 pi. Bless you. Now my original y's for cosine are 1, 0, -1, 0, 1. Eventually you just got to kind of memorize those. If I +2 to all of them, can somebody tell me what my new y values would be? Yeah.
3, 2, 1, 2, 3.
Yep. 3, 2, 1, 2, 3. And that's it. So vertical shift, that's all you gotta do. And now just make your sketch. It's a little easier to stay out of your way this time with your labels. I know I shifted it up, so I'll just write all my labels down low, and then I won't run into them. So I've got pi over 2, pi, 3 pi over 2, 2 pi. 1, 2. Just go by ones on my y-axis. That's good enough. So 3, 2, 1. Try to make it back at 2 and back to 3. So it's the cosine function shifted up. As far as a connection with sound, this is the only transformation. I don't really know of any connection with sound. So I can't really play that one. And the last one, if I were to do that, that would take the sine function and do what to it?
Subtract 3 and move it down.
Yeah, subtract 3 from the y's, it would shift it down 3. Don't do the opposite. We can go over one like that tomorrow if we need to. Okay, so the homework tonight, it's those 7 questions, but they're on a worksheet. So they're just up there, so if you're watching it in the video, you can see what the problems are. They're all on a worksheet for you.